Hi, my name is Manish Gupta, and in this video, I'm going to talk about internet augmented language models through few short prompting for open domain question answering. Right. So in the previous few videos, I've been talking about retrieval augmented language models. Now, in the same theme, here the idea is to actually do internet augmentation for those language models rather than augmenting using a small selected index of documents. Right. So the way this works is in three steps: retrieve, prompt, and re-rank. And we'll sort of understand what those steps are and what are we trying to achieve. Let's look at this picture. So let's say we are in the process of question answering. So here is the task. You have a question: who won the NFL football coach of the year? Right now, we can depend on the parametric memory that language models have so as to basically try and come up with an output answer. But that may or may not be correct, especially in case of temporal queries of this kind, where you are really looking for the NFL football coach of the current year in general, even though the user has not mentioned the current year. What these guys do in terms of internet augmented language models is to take this question and try to do a Google search with the question. Take the first few snippets that come in and essentially use them as passages. So you take those passages, you take those documents, you take passages from them, and then rank them appropriately, not just depend on the Google ranking, but actually do further ranking as we'll talk about. Rank those passages, take the most few relevant ones. Now, you take those relevant ones and use them to form a K-short prompt. So essentially, you have a K-short prompt and you basically provide the extra evidence that you've gotten from here, pass on your question, and then get an answer from the language model, get an answer from the language model. Now, after the language model generates answers, you can actually get multiple answers for the same evidence. So of course, you have several evidence paragraphs, and then for each of them, you have several answers. From them, you can further re-rank and then choose the best answer. Okay, so that's basically the recipe. Now let's look at some details. So basically there are three steps. One is retrieve. The second, this is the first retrieve step, first step. Second is prompt. So do the prompt, get the answers from the language model. And third is re-rank. Basically third is re-ranking. Okay. So in the retrieve step, the idea is given a question Q. This is the question, right? You retrieve a set of 20 relevant documents D from the web using Google. So they use the Google search API, but you can, the method is generic. You can actually use any language model and any search API, right? So, and then they created 60, and they created 6 sentence chunks out of them. So there are 20 documents and then 6 sentence chunks. So, and then what they did was to take Q, the question, and then the paragraphs, and they used a very simple similarity measure, TF-IDF based the cosine similarity measure. So you embed Q and the paragraphs using TF-IDF and use cosine similarity to produce a ranked list of, as you see here, a ranked list of evidence paragraphs. And then the idea is to basically take a top 50 from this ranked list of evidence paragraphs. These 50 you pass on to the next step, which is basically prompting step. So you use this 50 different evidence pieces to condition the language model through few short prompting. So few short prompting, specifically they use 15 short prompting. So you have 15 evidence question answer triplets, right? For these K-short prompting, they actually took question and answers from some of the existing data sets, and they also took evidence from those existing data sets. Okay, so that's how they have built K-short prompt, a 15 short prompt. And then what they do is to take each of those 50 different evidences that have come in and the question that is already existing so as to actually obtain multiple answers, right? So multiple answers from the same evidence. Okay. Now, once you get these multiple answers from each evidence, what you want to do is to select the best answer by re-ranking them using probabilities which are computed by the language model itself. So language model, when coming up with the answers, does come up with some probabilities. So can you use those probabilities so as to re-rank and come up with the best results that you see here? Okay. So how do you do this re-ranking, right? So there are various ways of re-ranking. So first way is very simple. You just depend on the probability of the answer that you come up with, given the paragraph evidence and the query, right? So that's basically the simplest way. That's the typical way of the ranking as generated by the language model itself. So this is not really re-ranking. This is basically just ranking as the language model would provide. But you could also re-rank based on some other techniques. For example, direct inference, which is also the method which is used in RAG. So the idea is you have to choose the answer which maximizes probability of A given Q. So you basically marginalize over n possible evidences, and where n is fixed to 50 here. But the idea is that you want to maximize the probability of the answer given the question by summing over different, 50 different relevant paragraphs. So where the first part of this conditional is basically TF-IDF based, and the second part is essentially coming from the model, from the language model. Okay. The second one is noisy channel inference, where the answer is chosen that maximizes probability of a answer, comma, question given the paragraph. So, and this is basically, applying Bayes rule, you can split it out that way, right? The third one is a product of experts, where they say that, hey, all of these probabilities, whether this one or this one, and even this one probability of the paragraph given query, all of these three could be really important. So how about actually trying to multiply these three, with some alpha, with something raised to alpha, raised to beta, and raised to gamma, where these alpha, beta, gamma are tuned using validation data. How about using all these three probabilities and then somehow coming up with a good re-ranking? Yeah. So that's their method. So basically, it's internet augmented language models where they get evidence from the internet and then they try to generate answers using the language model. Okay. So how do the results look like? So they experiment with 4 different data sets. 3 of them are question answering data sets, single hop natural questions, multi-hop hotpot QA, and strategy QA. And they also experiment with a 4th data set, fact checking multi-hop fever data set. Right? So the data sets have been chosen such that there is a good mix of single hop and multi-hop data sets. There is also a good mix of language generation versus classification data set. So natural questions and hotpot QA is language generation problem, while strategy QA is a 2-way classification problem and fever is a 3-way classification problem. They experiment with the Gopher as the language model. So they basically choose Gopher as the language model. And they essentially experiment with so many different size checkpoints of Gopher. So 44 million all the way to 280 billion in size. So 6 different sizes of checkpoints. Right? All of these checkpoints have been pre-trained using massive text 300 billion token corpus. Now, for each question Q, they generate 4 candidate answers A dash for each of the 50 paragraphs, leading to 200 answers. And then those 200 answers are re-ranked using these different philosophies that we talked about. This one, this one, this one, or this one, any of those 4. Right? And of course, they also compare with the closed book baseline. So where there is no evidences from Google coming in, it's just the Gopher language models which are being used to take the question and then come up with the answer straight off. Okay. So here are the main results on the 4 different data sets. So you see each of the row corresponds to the 4 different data sets. These are the state of the art values for each of those data sets, right? Now, what happens if you sample one answer versus you sample 200 answers, right? So essentially, one answer basically means that you essentially don't need a re-ranking step, but then you still can use evidence, right? So you use the evidence and you essentially just depend on one single answer, which has the highest probability of being output given the language model, right? So what you observe is that, and then CV is closed book baseline. So remember closed book baseline. So essentially what you observe is that whenever you apply Google-based internet augmentation, you see the results get better. Whether you sample one answer or you sample 200 answers, compared to the CV-based baseline, the open book baselines are much better. Compared to the closed book baselines, open book baselines are much better. Now, OB Gold is that baseline where you use the actual golden evidence paragraph, which is supplied in all of these 4 data sets. So use the golden evidence paragraph rather than depending on Google, depending on the retrieved paragraph by doing a Google search, right? So therefore, this is more like an oracle thing. This is not realistic in prediction scenarios, because in inference scenarios, deployment scenarios, nobody's going to give you the golden evidence anyway, right? So, but what you find is that compared to various other re-ranking schemes, you find that the product of experts re-ranking scheme works the best, right? Also, if you look at the retrieval performance, so remember you're also retrieving from the Google Search API, right? Various paragraphs that may make sense. What you observe is that the retrieval performance is really good for natural questions and hotpot QA, but not so good for fever and strategy QA. So retrieval performance actually is better for natural questions and hotpot QA, but not so great for fever and strategy QA. Right. This is the performance, as you can see, across different re-ranking schemes for each of the 4 data sets. So what you observe is that the product of experts basically gives you the best results, versus, if you basically just took the probability, the generation probability from the language model, that's basically the worst. So RAG is better and noise channel is even better. Product of experts is the best. What you see here is how does the scalability happen with the size of the model. So you see 6 different sizes of models, and you see on the y-axis accuracy. So what you observe is these horizontal lines are essentially random accuracy. So this is the chart for fever and strategy QA. So blue lines are for strategy QA, black lines are for fever. And what you observe is that especially in these fever and strategy QA, these classification kind of tasks, you observe that um, that the open book scenario sort of helps in the slightly larger range of parameters, right? Models with larger number of parameters. When you have smaller number of parameters, typically the dotted line and the solid line, which is basically, the closed book versus the open book kind of scenarios, they overlap with each other. So there's not much of a difference. But as you increase the model size beyond say 7 billion, 7 billion and 280 billion, you actually see improvements on the classification performance, right? But if you look at the generative kind of scenarios, hotpot QA and natural questions, what you observe is that even smaller models basically show significant gains using the open book scenario rather than the closed book scenario. Yeah. Now, the last comparison that I'm going to talk about is basically number of paragraphs to retrieve. So remember, we basically retrieved 50 paragraphs. What happens if you retrieve just, let's say, just 1 paragraph, 5 paragraphs, 15 paragraphs, and up to 50 paragraphs, right? So, so what you see on the y-axis is, of course, exact match, that's the accuracy. But what you see here as the curves is basically 1 billion model and 7 billion model curves. So dotted ones are the 7 billion model curves, and therefore they have better accuracies compared to solid curves, which have lower accuracies. Solid curves are 1 billion models, clearly, right? And why are there 4 curves? Well, the 4 curves basically indicate the kind of re-ranking mechanism used. And as you see, product of experts performs the best, right? So the horizontal line is the closed book baseline. So what you observe is that if you're using, let's say, the best model product of experts, best re-ranking strategy, then even 5 examples are actually 5 paragraphs which are taken as evidence from the internet augmentation are really good enough to reach that kind of accuracy with a 7 billion sized model compared to a 280 billion sized closed book model. Okay, so that's important. So 7 billion sized internet augmented model is equivalent to closed book 280 billion sized model in terms of performance if you basically use 5 paragraphs of augmentation. Okay. So let me summarize this video. Well, we talked about internet augmented language models. You can think of them as an extension of the retrieval augmented language models, where retrieval is being done from the internet, specifically using search engine. Right. 3 steps of doing this is retrieve, prompt, and re-rank. Then we looked at various re-ranking strategies, and they found that the product of experts outperforms consistently. They found huge gains in the open book setting compared to closed book setting across 4 different data sets. In short, searching the internet is worth more than 273 billion parameters, because as you observed here, compared to a closed book 280 billion parameter model, the 7 billion parameter model actually performs way better. Right. Okay, so hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.